Hello, my name is Edward Finkelstein, and my research project is controlling solitons, guiding particles from valleys to peaks with minimal motion, optimizing neural networks for soliton dynamics. This research project is in collaboration with Paul Belinsky, Roberto Marquez, and my advisor, Professor Carretero. The objective of this project is to control a particle in a potential energy landscape, which is formed by a confining parabola that confines the particle inside the landscape and a hump that can be shifted to the left and to the right with a neural network. Now, the challenge is to shift the hump from the left and to the right in such a way as to move the particle from the valley to the peak with minimal motion. The key insight about this problem is that it's analogous to controlling bright solitons, which appear in a variety of different physics applications such as plasma physics, Bose-Einstein condensates, water waves, and many more applications. The approach that we want to apply with this project, or the result of this project, is to use the variational approximation to reduce the nonlinear Schrodinger equation, which governs soliton dynamics, to an effective ordinary differential equation. So that way we can use a similar control mechanism to control solitons as opposed to particles. But this project is concerning particles. It's a stepping stone in that direction. Now, solitons in physical systems are ubiquitous. Namely, they appear in a variety of different physics domains. They're important because they're stable wave-like structures that maintain their shape while propagating, and they have various applications. Some of them are listed here. For example, in plasma physics, they can manifest as energy packets, like the manner in which energy is transferred in fusion reactors. This can be good if you don't want the energy packet to lose shape or form, but at the same time, this could also be a rogue wave that you need to control. You need to confine it within the fusion reactor. They can also appear in Bose-Einstein condensates, or rather as Bose-Einstein condensates, and these robust structures, when you're dealing with Bose-Einstein condensates, can be very useful for quantum state manipulation for sensors and atomic clocks, for example. Also in optical communications, they can be transmitted as signals in fiber optic cables. So it's very useful for transmitting data with minimal loss. But again, it's important to know how to control these things because, they're kind of like rogue waves in some sense. So the methodology we use to learn how to control these waves without actually going into a lab and trying to do it, which is expensive, is we just kind of looked at Newton's second law. Right? We just said, we looked at Newton's second law. It says mass times acceleration equals the negative derivative of the potential energy that we're considering, which consists of a confining parabola and a hump, which we're modeling as a hyperbolic secant function. Now, the neural network is the control function psi of t, which we wish to optimize to guide the particle from the valley of the landscape to the peak. And here's the neural network. It takes the current time in the simulation as input, and it outputs how much it should displace the hump from the center. Now, the loss function, which we use to optimize this neural network, it combines different constraints on the displacement function for the hill. So it combines constraints such as position, velocity, and smoothness constraints. So not only do we want to learn how to guide the particle from the valley to the peak, but we also want to do so in a way that doesn't involve any robust or not robust, but very abrupt movements or too much velocity. We want to learn how to do it smooth and efficiently. So this is what we learned. Right? So we were able to successfully guide the particle from the valley to the peak. So first it starts at the minimum. The hill shifts to the right, then it shifts to the left, and then it gets to the top. And it gets to the top in such a way that the hill and the particle are at the center and at the top. So it's in an equilibrium, an unstable one, but an equilibrium nonetheless.